So, welcome back student. So, this particular week we will try to discuss couple of similar strategies which we have already talked. We are basically discussing functional group based strategies, and the guideline 5 basically we are talking about FG based disconnection, and we are mainly focusing on how to introduce different kind of appendages or different kind of key functional group based appendages. Now, next particular problem is not a appendage based disconnection, but will be a relatively easier one. Now, I am trying to give you the target structure. The structure might look little bit complex to you, but nevertheless you will try to draw this kind of structure in a 3-dimensional form, and then the target which was given to you is having this structure. But the starting material we are also giving. The starting material which was given to you having a cyclohexane based core structure, and this part we are basically having a lactone. The remaining part all are similar. If you closely analyze through a skeletal disconnection approach or any other approaches, you will find that only thing is you basically deoxygenated the lactone in the starting material to complete the synthesis. So, in principle it is basically FGI or FGA, you can say functional group interconversion or functional group addition. It could be based on FGI or FGA. Now, the target was given a, this part is basically ether, it is a 5-member ether based on a cyclohexane framework. 5-member ethers are normally known as tetrahydrofuran. Now, the disconnection which will be now drawing here, if you have a compound something like this, if you are having a monotosylate of this particular or hydroxytosylate, you can simply do a intramolecular SN2 reaction by abstracting a hydrogen here to generate a alkoxide which can undergo a ring closing. So, this is basically a simple FGI. Now, try to correlate how this intermediate can be linked to this starting material. I say this intermediate can efficiently be constructed if you having this corresponding diol. Now, this diol will be having structure of this structure. Now, this can be easily prepared by a reductive cleavage of this starting lactone. So, synthesis which will be now we will go to the forward synthesis and will see how it can be done. The starting material was given a cyclohexane based lactone. The 3-dimensional drawing was basically given to give you a practice that you should start drawing that how these cyclohexane based compounds can efficiently be drawn in a 3-dimensional pattern. I say this compound will be now subjected to lithium aluminum hydride as a strong reducing agent, and you will get the corresponding diol. Fine. Now, this is a primary hydroxy and this is a tertiary hydroxy. So, we will just convert this to a 1 equivalent of tosyl chloride to the corresponding monotosylate, and monotosylate will be giving you this particular compound. So, OTS is the primary hydroxy group which is selectively reacting to give you the monotosylate. Now, this compound if you react with sodium hydride, it will basically initially generate the alkoxide. Okay. OTS, and definitely the allyl group is here, allyl group is here. Now, this O minus will now attack in a SN2 fashion, intramolecular SN2 to complete the synthesis through a simple intra SN2 type reaction, and then basically you will access the product. So, this is nothing, this is just a simple FGI, and this now completes the synthesis. So, what we did we basically analyzed the skeleton of the target and try to correlate with this starting material. The starting material was this one and the target was this one. You basically need a deoxygenation reaction to this lactone, and that was normally done through a intramolecular etherification reaction. So, now we will try to focus it out our final guideline for functional group based disconnection, the guideline 6. The guideline 6 mainly focused on redundant functionality. Now, redundant functionality we sometimes discussed, but not in detail. We said redundant functionality are those functional groups which is absolutely required for FGI, but they are not a part of the final target molecule. For simplification or simplified explanation, if I say I have given you a target molecule something like this, a cyclohexane, and I say the starting material which was given to you a cyclohexanone. Now, all of you know that this reaction can be done in a single step transformation named as Wolff-Kishner reduction. So, only thing is this ketone group will be now deoxygenated. Now, the starting material which has a ketone will be remain absent in the target molecule, because the final target does not have any active functional group. So, wherever you would find that the target molecule does not contain a active functional group, you need to introduce some functional group in the intermediate which act as a redundant functionality. Redundant means in reality it was not part of the final target molecule, which basically you need to introduce for the functional group interconversion, because you need some functional group for functional group interconversion. This is the concept of redundant functionality, and we will try to explore it with couple of example. The first example which we will pick is cyclohexane based compound, and normally when we are discussing this redundant functionality, you always find that the final target molecule may not have a active functional group. Now, this compound is a purely hydrocarbon, the target molecule, and see there are only 2 methyl appendages 1,4 position in a cycloheptane framework. So, we will explore the redundant functionality by introducing to CHO group. We say that the CHO group can be converted to the corresponding methyl group by the transformation which you already know. You can do a Wolff-Kishner type transformation, or you can do a Clemmensen reduction. This is already known to you, Clemmensen transformation. Fine. Now, this kind of functional group now you need to think about. Now, here as the target molecule have given, the starting structure was not given, it is fine. We will now let us simplify it, how this intermediate we can convert. The next retro which we are drawing is something like this. Now, what you say? We say if you have this kind of bicyclohydrocarbon with a olefinic unsaturation, you do a ozonolysis, here. Now, count the ring carbon 1, 2, 3, 4, 5, 6, 7. So, if you do a ozonolysis, this part is your CHO, this part is your CHO, which is act as a appendage. Okay. Now, why you have disconnected in this way? There must be some logic, that there must be some transformation which is already known to you, or some kind of transformation we already are familiar. Now, still we want to discuss it further and try to focus on the remaining part. Now, if you see the compound here, this is also a kind of there is no active functional group. So, here we bring another 2 functional group, which are also a redundant functional group, which will be removed, because in the target this is now target molecule which does not have this kind of functional group. Now, we all know if carboxylic acids are heated under strong thermal condition, they undergo decarboxylation reaction. So, in principle, if you do a decarboxylation reaction, you can end up with here. Now, to formulate this one, now we say we will be trying to give you a this compound as a diene and this compound as a dienophile, which will be basically the give you this particular compound. Now, initial visualization was difficult, but I say now try to visualize this in this way. This bottom ring is basically the 7 member ring 1, 2, 3, 4, 5, 6, 7. You have a double bond here, which basically can be coming from this diene part, double bond here, and this 2 things is now these 2 things. You have a maleic anhydride, so which will basically hydrolyze to give you this carboxylic acid. So, now you do the forward synthesis, then it will be quite clear. So, start with this diene, take this diene and react with maleic anhydride. So, basically what we will get, I will write in a different way as given in the intermediate. I will put this double bond here, which has been newly generated, and then we will this is the initial intermediate, which will basically get by a 4+2 cycloaddition or Diels-Alder reaction. Now, this will be just simple hydrolyze with a base, and that will give you the intermediate, which is our known intermediate, which we have earlier drawn. Now, the synthetic step demands both this carboxylic group needs to be removed. You do a very strong heat to decarboxylate those 2 carboxylic acid groups. And eventually, this 2 carboxylic acid group also serving as a redundant functionality. Now, here you come here. Now, see this 1, 2, 3, 4, 5, 6, 7. Even this ring also 1, 2, 3, 4, 5, 6, 7. Now, you are doing a ozonolysis reaction. So, ozonolysis basically clips this particular bond, and if it clips this particular bond, you will now getting this compound, is not it? Now, you do a Wolff-Kishner transformation or a Clemmensen transformation, which is pretty much known to you, I hope, and then you can basically complete the synthesis. So, here what we did basically, we use the concept of redundant functionality. We say that redundant functionality are those functional group which in reality is not a part of the molecule, but still you need to introduce those functional group in terms of a effective FGI. So, in this whole synthetic pathway you will find we used a carboxylic acid as a redundant functionality, we can call it redundant FG, as well as the final step we use aldehyde as the equivalent of methyl functionality. We introduce a methyl group and we started from a corresponding aldehyde, which we know can be done by either Wolff-Kishner transformation or Clemmensen reaction. So, until unless you know this Wolff-Kishner and Clemmensen, you will not be able to use the concept of redundant functionality for this molecule, and redundant functionality is a very nice demonstration of how a typical target molecule where you do not have a active functional group, you need to introduce the redundant functionality. On the same line, we will now pick up some other examples which will basically give you a conceptual clear cut idea of the entire topic. So, I said this is your target molecule. Now, the earlier one we haven't gave you the starting material. Now, I will provide the starting material. Now, I say the starting material is something like, not something, is exactly the same starting material. Okay. So, now if you basically consider, you will find that the no, it is a little bit wrong. So, this will be actually CHO, yeah, CHO. So, you see that starting material is a aldehyde containing group, aldehyde containing molecule, and the molecule which was given you as a precursor was having an extra ketone group. Now, try to correlate this ketone in the final target has to be removed. So, here basically this ketone is serving as a redundant functionality, redundant FG. Now, do a retro. Now, we say that there are actually, if you introduce a ketone, there is already aldehyde. Okay. So, now if you try to deoxygenate by Wolff-Kishner or Clemmensen reduction, ketone and aldehyde both can undergo such reductive reaction, and then your target will be something different. This aldehyde will be converted to methyl. So, we do not want that. So, means that you have to basically protect this aldehyde as a some of these protecting groups. So, the aldehyde activity will be suppressed. So, you start with the starting material and you protect the aldehyde first. Now, aldehyde protection, as you said, you can easily protect the aldehyde with ethylene glycol. You do the protection, okay. So, now the aldehyde is basically masked, aldehyde you are protecting it. Now, there is absolutely no problem in this Wolff-Kishner reduction. So, now you do the Wolff-Kishner reduction, the reagent is hydrogen hydrate and KOH was used as a base, and you reflux this whole thing, and then you will find that this part will be now deoxygenated. There are actually other ways to deoxygenate this ketone, but it is a very simple way. And if you remember the earlier slide, couple of earlier slides, we have talked about how the alcohol can be deoxygenated. So, in principle this ketone also can be reduced to give you alcohol, then alcohol can be converted to tosylate or mesylate and then use the superhydride Li83BH or even sodium borohydride, that can also deoxygenate by a hydride attack. So, now only thing is you basically require the removal of this protection group. So, which can be simply done by this acidic workup and you come to your target molecule. So, this kind of simple functional group interconversion by taking the help of a redundant functionality often helps, and whenever your molecule there is probably a dearth of functionality, we sometimes call dearth. Dearth means there is absolutely no functional group present, dearth of functionality. So, in those cases the redundant functionality is very helpful and we will try to explore the redundant functionality with couple of more example. We give a target which is now basically a salt, a phosphonium salt, which is often used in the Wittig reaction. This is your next target and you are exploring the concept of redundant functionality. The starting material which was given to you this one. Now, I say if you try to correlate, this compound is having a furan ring and a 2 position, you having a 3 carbon extra CH2, CH2, CH2 and the starting material is having a perfural 2 position of the furan, you are having this aldehyde group. Now, conventional retro probably will give you the first intermediate which you basically need the corresponding iodo. Iodo you reflux with triphenyl phosphine to get the viticulite. The iodo we can easily synthesize by using a very standard FGI Apple reaction, which you have Apple transformation, which you already discussed this. Now, try to correlate, this is 1 carbon, you need to introduce 2 carbon extra and this 2 carbon extra probably you can think about by using a Ampolong type of chemistry which you have already discussed. We say if you have this compound which is basically nothing, a furfural have been protected as this 1,3-dithiene. Now, you can easily abstract a hydrogen through base. Now, do this forward synthesis. So, start with the furfural, react with 1,3-dithiene. So, initially the aldehyde will be basically protected as its dithiene. Dithiene, the remaining hydrogen is extremely acidic. So, react with LDA and you generate the corresponding lithiated species which is serving as a Ampolong minus lithium plus. Now, as you need to introduce 2 carbon extra, you react with a epoxide as a electrophile. You find that this epoxide reacts very nicely and then you make the this. Okay. So, 2 carbon extra addition was done, but in the final product this 1,3-dithiene was not required. So, now this 1,3-dithiene is surplus extra. So, now you need to remove these things with some reagent. Now, if you remember the earlier very beginning part of our lecture, we talked about sulfur can be easily desulfurized by a reagent named Reanalysis. So, Reanalysis will essentially reduce this sulfur thing and to give you a CH2. Now, this particular reduction sometimes referred as Mozingo reduction, Mozingo type of reduction, which is basically nothing. If you having a dithiene, you react with Reanalysis hydrogen, you basically get the corresponding hydrocarbon. So, now see we are here, now you do the Apple reaction, triphenyl phosphine and iodine, sorry we have the final compound iodine, yeah fine. So, then you get the Apple thing and then reflux with triphenyl phosphine again to complete the synthesis. So, you can basically get the corresponding phosphonium iodide as a salt, and this is your target molecule. So, here is basically a combination of transformation based approach where you used a synthetic equivalence. The synthetic equivalence concept we have earlier explained, and synthetic equivalence as well as we use redundant functionality, redundant FG. So, redundant functional group in that way is a very nice demonstration. Whenever your molecule does not have any active functional group, you can think about bringing some extra functional group in the intermediate stage, and then depending on your final target, those functional groups can be removed. Functional groups can be removed because those functional groups are not required, those are surplus, but you need to bring those functional group, because without functional group you cannot think about a retro. As I said, the retros always need to be based on a functional group, as we are discussing functional group based retros. So, we will keep on our discussion or keep on continuing our discussion on these redundant functional group based approaches in the next week. Till then, have a good time and goodbye.